Till long day after, today I will discuss Liouville's theorem. We all of us know Liouville's theorem. In my previous video, I had discussed many video about Liouville's theorem, many exercise about Liouville's theorem. Today I will discuss Liouville's theorem as just a review, because Liouville's theorem in complex analysis is very important theorem and all result is very important for any competitive exam. So as a review today also I will discuss Liouville's theorem. What is the statement of Liouville's theorem? Every entered and bounded function is constant. We all of us know. That means when f is defined from C to C is enter plus bounded, then f is constant. That means every non-constant enter function always be unbounded, and every enter function is bounded on every bounded region. That means if D is bounded, if the domain is bounded, then FD always be bounded. Next I will see extension of Liouville's theorem. I had seen in my previous video extension of Liouville's theorem and proof of extension of Liouville's theorem. Just as a review, today I will discuss the statement of extension of Liouville's theorem. If f is defined from C to C, which is analytic, then there exists always alpha greater than 0 and r greater than 0, such that modulus of fz less than equal to k times mod z to the power alpha, where modulus of z greater than r. That means extension of Liouville's theorem, if this is mod z less than r, then extension of Liouville's theorem is true for mod z greater than r. Then always fz is polynomial of degree at most alpha. This is the greatest integer, because degree of the polynomial 1.5, 1.8 not possible, only 1, 2, 3, 4 this is possible. Okay, if you don't see my previous video, at first see my previous video. I had proved extension of Liouville's theorem elaborately in those video. Now I will see one diagram. This is very important. Analytic means this is differentiable. Differentiable means this is continuous. Continuous means this is integrable. Integrable means this is bounded. This is not if and only if condition. This condition is true, and if analytic, then this is differentiable, then this is continuous, then this is integrable, then this is bounded, but converse not true. If fz equal to mod z square, then it is differentiable but not analytic at the point 0. If fz equal to z bar, this is continuous but not analytic. So converse is not true. And this diagram is very important diagram. Analytic imply differentiable, differentiable imply continuous, continuous imply integrable, integrable imply bounded. There exists a nice theorem: if f be defined from complex number to complex number, be analytic, and D is a bounded subset of C such that for all z belongs to C, there exists z dash belongs to D such that f of z equal to f of z bar, then that implies fz is constant. That means If this is the point z and z bar, then always for all z belongs to C, in z be the member of complex plane. For this z, there exists always z dash belongs to in the domain where D is the bounded subset of complex number. Always there exists a D such that f of z equal to f of z bar. For this z, always there exists one z bar such that f of z equal to f of z equal f of z, and this is f of z bar. F of z equal to f of z bar. Since for all z belongs to C, there exists one z bar, at least one such that f of z equal to f of z bar. So that implies f of C equal to f of D, and since f of D is bounded, that means that implies f of C also be bounded. And if this f be a function from complex to complex be analytic, that means this is entire, and entire plus bounded, that imply function f is constant function by Liouville's theorem. Therefore f is bounded on C. So by Liouville's theorem, fz is constant. This is the proof. If f be a function from C to C which is analytic and D is bounded subset of C such that for all z belongs to C, there exists one z bar such that f of z equal to f of z bar, then f of z is a constant function. Now I will see what is the Picard's theorem. Every non-constant entire function always omit at most one complex number as its value. If an entire function omit two or more value, if entire function omit two or more value, then always it become constant function. As for example, if fz equal to e to the power z, then image would be e to the power z minus singleton set 0. Since it omit only one point, so this is non-constant entire function. But if it omit two or more values, then it becomes a constant function. Fz equal to sin z, cos z. Here fc equal to whole complex number. As for example, I will say one question which had come in CSR NET June 2016 exam. Let f be non-constant entire function. Then which of the following properties is possible for f for each z belongs to complex number? Option 1, real fz equal to imaginary fz. Option 2, absolute value of fz less than 1. Option 3, imaginary of fz less than 0. Option 4, fz not equal to 0. Consider this is u axis and this is v axis. If real fz equal to imaginary fz, that means u equal to v, and u equal to v means these lines, straight line who is passing through origin. Notice here range omit infinitely many points. Since range set omits infinitely many points, so By Picard's theorem, fz is a constant function. And here the question, which of the following is non-constant enter function? So this is wrong option. If second option modulus of fz less than 1, that means function is bounded, and this is fb enter function. Enter plus bounded imply constant. So option B also wrong option. Option 3, imaginary fz less than 0. This is the u axis, this is the v axis. Imaginary fz less than 0 means v less than 0, and this part would be this part. Also it omit infinitely many points from fz, so by Picard's theorem this is not also true. That means only option D, fz not equal to 0. When fz not equal to 0, this is the non-constant enter function. I hope my all viewers have understood how Picard's theorem be useful. Okay, well. Next I will see fb enter function. Then which of the following statement are correct? Option 1, f is constant if range of f contained in a straight line. Option 2, f is constant if f is uncountably many zero. Option 3, f is constant if f has unbounded on the set z belongs to C such that real z less than 0. Option 4, f is constant if real part of f is bounded. We all of us know application of Liouville's theorem. First application of Liouville's theorem, if f be complex number to complex number, be holomorphic function, if u holomorphic function is fz equal to u plus iv, if u be the bounded function, then fz always be constant by Liouville's theorem. And we have to prove it by constructing gz equal to e to the power fz, where fz equal to u plus iv. Just see the proof. This is very simple proof. I had elaborately discussed in my previous video. Similarly, if vxy, if imaginary part is bounded, then fz is constant. Here we have to construct gz equal to e to the power minus ifz. Next, if au plus bv greater than equal to c, or if au plus bv less than equal to c, then for some constant a and b, then fz has to be constant. For this we have to construct gz equal to a minus ib times u plus iv, and this is equal to capital A times fz, where capital A is a constant function. Notice here gz is obviously enter since fz is enter, and real gz equal to au plus bv, and since given au plus bv less than equal to c or greater than equal to c, so this part would be less than equal to c if you consider less than part, then that imply real part of gz less than c means real part of gz bounded. Since real part of gz is bounded, that imply gz is constant function. Since gz is constant function, that imply fz, since gz equal to a times fz, so a times fz, so this would be constant. And here the question, f is constant if range of f contains straight line. Range of f contains straight line means straight line look like? Ax plus by equal to c. That means here would be au plus bv equal to c. This is look like this type. We all of us know if au plus bv is greater than equal to c or less than equal to c, then fz has to be constant. By this part we have to tell f is constant function. Also, since the range of f contains straight line, any straight line, by Picard's theorem also we can tell this is constant because it omits infinitely many points from range of f. Next, f is constant if f has uncountably many zeros. We all of us know identity theorem. If uncountably many zeros has limit point and if this limit point contain in the domain, then we can tell function is constant. But if we consider fz equal to sin z, we all of us know sin z equal to 0 at n pi points. That means f has uncountably many zeros, but f not be constant. So option 2 is wrong option. Option 3, f is constant if f is bounded on the set z belongs to C such that real z less than 0. Real z less than 0 means x less than 0. If you consider e to the power z, then this would be e to the power x time plus iy, and modulus of fz means e to the power x times e to the power iy. This part would be, since x less than 0, this part would be less than equal to 1. Notice here f is constant if f is bounded on this set. Obviously f is bounded on this set, but e to the power z is non-constant entire function. So by this construction we can tell this option also wrong option. Option 4, f is constant if real part of f is bounded. We all of us know by Liouville's theorem, if real part of f is bounded, then fz always be constant. That means option 1 and option 4 is the right option. Now I will say some application of Liouville's theorem. Let f be entire function and d be subset of C, so then fd is bounded. We all of us know in real analysis, in continuous function, if f defined from R to R, if the function is continuous and domain is bounded, then always range fr would be bounded set. It is applied in entire function. If f be entire function and d be bounded set, then bounded subset of the complex number C, then fd always be bounded. Next, if f equal to u plus iv be an analytic function in the extended complex plane. If the function is analytic in the extended complex plane, then fz is constant function. And third, if fz is a non-constant entire function, then always the range set would be dense in complex number. That means if fz equal to this subset, then fz bar always equal to whole C. Its closure always equal to whole complex number, because when fz is non-constant entire function, this is necessary. For constant this is not true. When fz is non-constant entire function, then always range set is a dense in complex plane. Okay? Oh well. Next question, f be defined from complex number to complex number which is entire function. Suppose that f equal to u plus iv, where u and v are the real part and imaginary part of the function respectively. Option A, uxy such that z equal to x plus y, iy belongs to complex number is bounded. If real part is bounded, then obviously f is constant. Because the question about when f is constant, if in which condition f is constant. Here real part is bounded, then f is constant. Here imaginary part v of xy is bounded, obviously this is constant, imaginary part when constant. Here u plus v is bounded, then I have seen if au plus bv less than equal to c or au plus bv greater than equal bounded above or bounded below, then this implies this is f is constant function. Here a equal to 1 and b equal to 1. So u plus v is bounded, that means obviously function f is constant. Here u square plus b square is bounded, then f is constant, obviously. Here f equal to u plus iv, then mod f square equal to u plus iv whole square, this is equal to u square plus v square. If this is bounded means this is m. If mod f square less than equal to m, then obviously f less than equal to m, and if f is bounded, since given f is entire function, so obviously this is by Liouville's theorem, entire plus bounded, this imply always constant. So this also right option. That means option A, B, C, D all are right. All are constant, imply constant function. Today I will stop here. In my next video, I will discuss identity theorem of complex number. Okay? See you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.